It is interesting how two separate fields can in fact be connected. Even more so, it is strange how one can prove an unprovable theorem by doing something completely irrelevant, or so it would seem, to the problem. However, there is a method behind the madness, and it is probably one of the most powerful ways of thinking, not just in mathematical problem solving, but in problem solving in general. By the end of this video, you will know this way of thinking, hopefully. Fermat's last theorem. It was one of the most difficult solved problems in mathematics. It was proposed in 1637 when Fermat wrote in the margin of a book his conjecture, and that he had a proof for it, but could not write it. He then died. Since then, for 356 years, it was unsolved, until mathematician Andrew Wiles gave a magnificent proof for it in 1993. However, 77 years earlier, a Russian mathematician, Schur, attempted to prove Fermat's last theorem. This resulted in many theorems, which today are known as Schur's theorems. However, while his attempt failed, his new theorems revolutionized many fields of mathematics. One theorem in particular, Schur's theorem of Ramsey theory, was particularly interesting. It was regarding the nature of addition in a balanced set of numbers, and yet it was proven by coloring triangles. Not only that, but it connected two fields of mathematics, and even fathered its own field. The theorem was purely about sets and addition between numbers, with nothing to do with graph theory, geometry, or colors. And yet it was proven by coloring triangles and finding the color of nodes on a graph. Now, let me clarify. In graph theory, a graph is not a function or a relation graph on a plane. It is a set of vertices or nodes and edges that connect nodes. Now, back to the theorem. This seems to make no sense. How can the color of triangles in a set of points and lines give truths about the nature of addition and possibly even solve Fermat's last theorem? However, by the end, you will know why and how this can be, and you will be a better problem solver in the process. This is not just about numbers and colors. This conveys a larger lesson about mathematical thinking, and how changing a problem and linking ideas is one of the most important skills in mathematics and the sciences. So what is this remarkable theorem? How does the color of graphs and triangles have to do with it? What is this connection between graph theory and additive combinatorics? And what is this idea of mathematical thinking? First, we need to understand Schur's theorem of Ramsey theory, the remarkable theorem I mentioned earlier. The mathematical vocabulary is somewhat high here for the average viewer, so let us break this down. This partition of a set S is the set of non-empty subsets such that all elements of S are in the new partition. Each subset is called a part. For example, the parts of the set 1, 2, 3 are set 1 and set 2, 3. It could also be set 1, 2 and set 3. It could also be set 1, 2, 3. In either way, all of the elements of the set are in one of the parts. You could assign any element of the set to one of the parts, and it would be in one of the parts. It is also important to note that there could be multiple partitions for a set, as shown here, which is important because our theorem says if it was partitioned in any way possible. Also, what is this bracket n? Bracket n is, in Ramsey theory, the set of all integers from 1 to n, as shown here. Now back to this theorem. Choose any positive integer r. For any r, there exists a positive integer n such that if bracket n was partitioned into r parts in any way possible, one of the parts would contain positive integers x, y, z, such that x plus y equals z. What does this mean? Choose any positive integer r. There exists a positive integer n. If we were to partition the set bracket n into r parts, Schur's theorem tells us that in one part, two numbers, x and y, will add up to a third number of the part, z. In order to prove Schur's theorem, we need to know of another theorem, devised by Frank Ramsey. Today, it is called Ramsey's theorem. For every positive integer r, there exists an integer n, such that if the line of Kn, a graph with n nodes, are colored with r colors, then there is always a monochromatic triangle. So that means for any amount of colors that we color a graph with n nodes, where n is a certain positive integer, there's always a monochromatic triangle, which means the triangle has the same color on all three sides. Thought. Whenever we see a problem anywhere, we always think about the problem. If we just analyze the problem enough, we can find a solution, we say. But what if the right place to think was not the problem? What if, in order to solve the problem, or to ask the question, we need to think about our view, or the perspective, of the question or problem? This is the key principle to the most beautiful, elegant, and revolutionary insights and solutions in mathematics, natural and social science, engineering, philosophy, and basically everywhere, even in daily life. Think about our view of Schur's theorem. How do we see it? We think of it as the statement that there is a part of a set between 1 and n, such that for all positive integers, there exists an n. Focus deeply on the partition part. We are seeing parts as sets. Think about how difficult it would be to prove this. There exists a set from 1 to a certain number, such that two numbers of a part add to the third number of a part, for all possible number of parts. How would we prove such a thing? We could bash our heads against a wall forever. However, what if we could change how we think about parts? Well, first, we need to retain the properties of a part. If we don't, then we cannot change our perspective without sacrificing something and ruining the proof. A part is a type of subset of the set, where the union of all the subsets creates the original set. By definition, you can assign numbers in a set to a part. The last one is key. The fellow mathematician solving this would make an important connection here. Colors. We can represent a part of a set as a set of nodes in a graph that are colored, where each node represents a color. The key insight here is to color the members of bracket n in such a way that the members of each part have the same color, as shown here. This way, parts become colors. Now, we can rewrite the problem to, for all positive integers, choose any positive integer r. For any r, there exists a positive integer n, such that if a graph with n nodes is colored with r colors, then there exists a monochromatic, meaning same color, solution to x plus y equals z, meaning x, y, z are all monochromatic such that x plus y equals z, where x, y, z are all elements of bracket n. And in a graph with n nodes, we want to number each node from 1 to n. Here, a monochromatic solution of x plus y equals z means that x, y, z are all monochromatic and that x and y add up to z. What does this mean? Take any positive integer. Call it r. There is a number of nodes where each node is numbered from 1 to n on a graph that can be colored with r colors, such that two nodes with the same color add up to another node with the same color. But before we can prove Schur's theorem, we should probably create some notation so that we can organize all of this abstract information. Let phi of n be a function that determines the color of a node, given that n is the integer that represents the node we want to color. So, the integer that represents the node will go into the function phi and will spit out the color of the node. Also, if we want to mention the edge that connects 2 points, say P1 and P2, then we can write it as P2 minus P1 if P1 came before P2. From here, we can finally take on the beast. With Ramsey's theorem and a new perspective, we can now prove Schur's theorem. First, let's analyze the claim. We want x plus y equals z to be monochromatic. This should remind you of a triangle. If each side of a triangle is a vector, then two sides add up to the third. So we first want a monochromatic triangle. So color the edges of a graph. Also color the nodes of the graph, since that is what our written theorem is asking about. By Ramsey's theorem, there exists a number of nodes where there is a monochromatic triangle. In this case, let the triangle be on nodes A, B, and C. We can do this because our problem says that there exists a number of nodes, which Ramsey's theorem also says. Here is where we use our notation. Remember, phi of n tells us the color of the nth node. Each edge can be written as the second node minus the first node. So, if the triangle is monochromatic, it must have the same color for all sides, which means that phi of b minus a equals phi of c minus b equals phi of c minus a. Notice that b minus a plus c minus b equals c minus a. Now, let x equal b minus a, y equals c minus b, and z equals c minus a. Thus, b minus a plus c minus b equals c minus a becomes x plus y equals z. Also, phi b minus a equals phi c minus b equals phi c minus a becomes phi x, phi y equals phi z, which, if you remember our notation, will mean that this means they are the same color. Thus, for some n, x plus y equals z is monochromatic, which means that x, y, and z are all the same color. Since this all belongs to colors, then we can bring this back to the original Schur's theorem of Ramsey theory. Each color was meant to represent a part. If x plus y equals z is monochromatic, then it is the same color, which means it is the same one part of the partition of bracket n. Thus, the statement is proven. QED. Schur's theorem had a lasting impact on mathematics. It served the basics for additive combinatorics and revolutionized Ramsey theory. In 1927, van der Waerden proved a result regarding arithmetic progressions in numbered graphs. In 1953, Klaus Roth proved a theorem regarding how subsets following a certain limit always contain an arithmetic progression with 3 terms. In 1975, Andreas Meredi, which I'm definitely pronouncing wrong, proved a theorem that described the relation between a subset of certain types of integers and arbitrarily long arithmetic progressions. That theorem was changed by Hillel, Furstenberg, and Nietzsche Nelson, where they changed it into a theorem of geometry and then generalized it to all the dimensions. These two theorems were generalized by many, including Andras Sarkozy, which I'm definitely pronouncing wrong, Vitaly Bergelson, and A. Leibman. In 2008, Terence Tao and Ben Green used all of these theorems that sprouted from the sum of two numbers in the partition of a set to prove that primes contain arbitrarily long arithmetic progressions. It is purely amazing how coloring triangles could explain how two numbers in a part of a set add up to a third, which could be used to prove that the primes contain arbitrarily long arithmetic progressions. This all started with coloring triangles and pondering how two numbers in a part can add up to the third number of that part. This theorem connected two fields and even founded a field. However, the proof was so simple. How could this possibly be? People who achieve this must have superhuman abilities, right? Right? If you were paying attention, you might have noticed some text waving in the corner. This journey was full of many things. The first thing were connections that arose from recognizing patterns. We made the connection between colors and parts of a set. We made the connection between graphs and sets. We made the connection between addition and triangles. We made the connection to Ramsey's theorem. This was full of connections. Without making these connections, the important insights we had would not have been made. Any problem solver will know that insights are what solves problems, not banging your head on a wall. These connections were all made by recognizing patterns. We analyzed the parts, and then from there, we spotted a pattern, which led to a connection. This is also important in theoretical physics. Jeff Bezos even mentioned this in an interview. We also had to know a different theorem, and then had to make a connection to it. Knowledge of mathematics is important. It helps make connections to other theorems, which can be used to solve harder problems. But the most important element of all this begat the most important insight in this whole journey. The insight that parts could be represented as colors is by far the most important insight in this whole journey. This started with a connection, but that connection begat a new perspective. That is the most important element in mathematics, the sciences, and beyond. A new perspective. That new perspective rewrote an almost unprovable theorem into a theorem that was trivial using knowledge of other mathematics. That was the cause for the biggest insight in. With a new perspective, a new and much easier problem can be written. The proof of this really hard theorem arose from rewriting the problems into a trivial one, which arose from three things: connections, recognizing patterns, knowledge, and also new perspectives, which is the most important one out of them all. Now, how do you get a new perspective? Pure luck? If you were to remember earlier, before we rewrote Schur's theorem, a hypothesis was proposed, in which instead of just thinking about the problem, we also thought about our view and perspective on the problem. That, combined with the ability to make connections and recognize patterns, is how one arrives at new perspectives. A new perspective, combined with patterns, connections, and knowledge, is what solves problems. That is how people solve the hardest of problems. Easy problems can be solved with narrow thinking. Hard problems can be solved by actually thinking about the problem. But the hardest problems are solved by thinking about the perspective and the view of the problem. In fact, all of these are interlinked. Patterns lead to connections. Connections lead to a new perspective, as the connection between colors and parts led to the new perspective of the set. New perspectives also cause more connections, as can be seen by the connection between addition and a triangle. Without the new perspective, we would never even have reached that insight in the first place. All of these are interlinked. Throughout this plane of existence, there are always problems. These problems are tremendously difficult. We wish these problems were easier to solve, However, maybe a new perspective is what is necessary for the big problem to become smaller. Maybe a new way of looking at the problem will make the problem easier. Think about that. Just changing the way you look, see the problem makes it easier. That is a dangerous ability. That can solve even the hardest of problems. Doing that will require the ability to recognize patterns between concepts and make connections between them. As such, one can change their view of the problem and make it easier to solve it. We always think about the problem, but what if the major insight did not lie in the problem, but rather in thinking about the perspective of the problem?